15 to 20 years have come with a polyurea grease. Polyurea grease is ideal for electric motors. It's good to approximately 300 degrees F. Most of your energy efficient motors, the outside skin temperature on a day that it's going to be 100 degrees outside, the outside skin temperature will be up to 200 degrees. The grease is good to almost 300, 298 degrees. Polyurea grease is only compatible with one other grease, and that is calcium complex grease. The grease, what makes up the grease, say if a lithium grease uses clay as a thickener. A lithium grease is a good grease where water is present. However, lithium grease will actually absorb water and hold it. When the electric motor is then turned off, it'll have encapsulated water in the grease, which will get onto the metal and then corrode the metal. Next time it's started up, then you're beginning on with a bearing failure. Polyurea grease will dissipate the moisture out of the grease. And that's one of the reasons the manufacturers use it. The other reason is it is more resistant to electrical discharge. Electrical discharge has become a pretty serious bearing problem because of variable frequency drives and also on 3600 RPM motors. 3600 RPM motor has a problem with circulating currents. And circulating currents are they derive from the speed of the motor and the rotor bar count versus the stator bar count. The number of slots in the stator, number of slots in the rotor. And the circulating current will go to ground somewhere. And it's either going to go to ground through the shaft, to the coupled piece of equipment, or through the bearing. More likely it goes through the bearing. And when it goes through the bearing, it causes arcing, also causes the grease to deteriorate. As soon as that starts, essentially the bearing's over with because it's on a downhill run from then on. When we're greasing motors, when you apply the grease to them, everybody asks, how much should I put in? That's an impossible question to answer. On a pre-NEMA motor, it may have a grease pocket inside that may hold 6 or 8 ounces of grease. On a modern motor, you may be able to only hold 2 ounces of grease. So the frequency that the motor has to be greased is much different, pre-NEMA to NEMA. Pre-NEMA motor is 1960 and earlier, let's say. Actually, NEMA started 64. The transition actually was probably in the early 70s when it was finished. That's when everything became standardized. The greasing situation, if you apply a lithium-based grease and mix it with a polyurea grease, the thickener in the lithium grease will turn hard and it'll almost become like almost like a gravel inside. The bearing at that point is on the way down and you're not ever bringing it back by putting fresh grease in it. The recommended way to grease an electric motor is to remove the grease drain on the bottom side of the bearing pocket, start the motor, run the motor till the motor's at operating temperature, then lubricate it with the drain pocket out, with the drain in the bottom of it, the plug out of it, and then operate the motor for 2 hours to allow any separated oils and greases to come out the bottom. Then put the plug back in. Your greasing intervals, the pass out here that I told that we sent out, has some lubrication intervals in it. But again, you have to use your own common sense because some of the motors that you're working on are 30 years old, some of them are 2 years old. You have to pay attention to what you're doing. Using a hand-operated grease gun, all manufacturers, that is what they recommend to use. A battery-operated grease gun is great for the convenience, but you don't get the feel, the pushback, when the bearing's full. If you put too much grease in it, it overflows the grease seal to the inside of the motor, The grease slings out, gets on the windings. Eventually the windings go to ground. The motor's gone. You're down to a rewind. Also, if you put too much grease in a bearing, it'll also cause a problem. A grease fill in a bearing should be approximately 1/3. If the bearing's standing upright, it should approximately be 1/3 of the bearing. Any higher than that causes the grease to foam. The balls are spinning so fast, and it's beating the grease up. It's whipping it into a foam. And when it does that, then the bearing has higher resistance, and the bearing gets hot. And then once the bearing gets hot, the grease expands, and it moves out of the grease pocket into the motor. So you can put too much grease in one. A lot of people feel like they need to pack the grease cavity until it's full, and that's just incorrect. Too much grease is almost as bad as not enough grease, and it's a waste of energy. The power it takes to run an electric motor is greatly increased when the bearings are packed with grease. So approximately 1/3 fill, and that's, again, the bearing's hidden. You don't get to see it. You've walked up on the motor. You don't know what's going on. You just know that you're there, and you think possibly it's time to put some grease in the motor. Well, from that standpoint, a person maybe should use 5-6 pumps and call it good. But on a motor that's a 2 horsepower, a 5 horsepower, you might be looking at 1 pump. You get a 600 horse motor, you might be looking at 25 or 30 pumps. You know, it requires a little common sense when you do it. The issues that we're having with bearings and transferring the power, the electrostatic energy that the rotor's collecting from drives, you actually have to get that power to a ground somehow. And it's easy. The easiest place for the motor to take it to ground is through the bearing, and that will ruin the grease. I've got an example of a bearing here when we're all finished that you can come take a look at that is a pre-failure, where the grease is actually starting to burn from an electrostatic failure within the motor. The lubricants that we're using these days, we can get synthetic lubricants. You can spend as much money as you want on it. If you stick with a standard polyurea grease, and every manufacturer makes it, and don't mix your greases, you'll end up with a lot better level. And the polyurea grease, another reason that the electric motor manufacturers use it is because it's more energy efficient. It takes less power to turn that bearing with a polyurea grease than it does a lithium complex or a sodium or an aluminum-based grease. The only time you vary from that is when a manufacturer has designed into a motor a specific lubrication. And you find that sometimes on roller bearings. Sometimes you'll find a roller bearing on an opposite drive end. Usually on a belt-driven motor, you'll find a roller bearing on a drive end of the motor. Some motors you're finding now, the opposite drive end will have a roller bearing in it. When you see this on the motor plate itself, it usually has a specified grease. And some of them are using grease with molybdenum in it, and they're using it in the roller bearing. Where in the other end, where they have a ball bearing, they'll be using polyurea grease. Well, just need to be aware that in some situations now, you're going to find 2 separate greases in the same motor. And if you mix them, there's a good possibility you're on the way out with the bearing. And that is the highest failure rate.
So,
When
so
motors...
are you open for questions yet?
Sure.
How would we know, if we walk up on the motor, how would we know there's 2 separate greases in it?
You're not going to know. It's just going to have to be policy of what your people that are in charge of lubricating those motors, what they have to use. If they're, if you're going down to the parts store and you're buying EP2 chassis grease and then going out and putting it in a motor, if you put that in a motor that has a standard bearing in it that has polyurea grease in it, the grease is going to deteriorate pretty quickly, and you're going to start down the road with a bearing failure. That's just the way it is. A lot of bearings, when motors come into the shop, we find bearings where the races, when the motors are assembled, when the ends are put on the motors, the race, outside race, may cock in the end of the motor, end of the bearing. And in the end bell that's holding that race, when the motor goes out the door, when somebody rebuilds it, when the manufacturer makes it, it may pass test. But if it fails prematurely, by cutting the bearing open, where you can see the track that the balls have taken, you can tell whether that was a bearing race problem, whether it was a thrust problem. If you see the ball track all on one end of the bearing, so the ball track is all on one side of the race, then you know you have a thrust problem. Could be when the motor was installed, the coupler was too tight, had pressure against it, pushed the shaft back and pushed up against the bearing, and that'll burn a bearing up also. There's another thing that we're all facing now. When we dealt with pre-NEMA motors, there was a lot of iron in them. They were very heavy. When you put it on a skid, and you put your 4 bolts in it, you tighten it down, chances are the skid came up to match the bottom of the motor. Because there was so much iron in the motor, it wasn't going to give. Well, now, modern motors, they've taken a lot of the weight out of the motors. A lot of the iron's missing that was in them. And so now, if you get on a skid that is uneven, and what the manufacturers call this is soft foot. You set a motor on it and you see daylight underneath 1 foot. When you tighten that down, that 1 foot will settle. When it does that, the line bore that the bearings chase is now off. It's twisted the frame of the motor. So it's very important when you're setting a motor on a skid that you at least take the time to try to see if there's any air gap between any of the feet, and then use the appropriate shim to take that air gap out, because it's actually twisting the motor cases. Changes the line bore of the shaft, and we run into that pretty frequently these days. Also, when you mount a motor on a base, if the base is not clean or the motor feet are not clean, and you tighten it up, the same thing can happen. And I'm sure when you all go out and you're trying to install a motor and it's it's less than perfect conditions, and you're trying to get the belts lined up, and your thoughts are trying to get everything in line, probably the last thing you're looking at is the bottom of these feet. But it's important for how long that motor is actually going to last, how long the bearings are going to be able to stay in it. I can go on for hours about the different kinds of bearings and the problems. Anybody got any questions about any particular thing?
You said that at one point, I think, that there was a plate on some of the motors that would tell them what type of grease to use.
Right.
If there's 2 different bearings. Is there a
Correct. It's
question about it?
it'll either be on the nameplate, or they'll have a dedication plate on one end or the other that'll tell what the motor manufacturer or the equipment manufacturer specifies. For instance, P&H Crane Company, they specialize, or they specify a special grease, which is a calcium compound, lithium, molybdenum grease. There's only 2 manufacturers in the whole world to make. And you can't change up. If that's what that motor's got in to start with, and you put a different grease in there, you're going to have a bearing problem. It may take a while, but it's going to happen. It's a chemical reaction. And once you introduce the odd chemical, once you introduce that to it, it's on the road, and it's going to happen. It may take a while, but it's going to happen. 3,600 RPM motors, they have what they call an L10 bearing life. And at 24 hours a day, that bearing that's in that motor, if it's maintained, ought to last 3.5 years, running at 3,600 RPMs. And an L10 bearing life is the minimum that they're saying that could last. Now, if the temperature rise stays down and the lubrication stays correct, that bearing may run 10 years. But sometime when you have a chance, it's a good idea to study what they call L10 bearing life, because that is probably a military spec that started out through a long study of how long bearings should last.
I believe.
Yeah.
Okay.
Because you mentioned different sides of the motors having different types of lubricants.
Correct.
I'm actually gonna have two questions here. But the first one, could you suggest, since this polyurea lubricant sounds like it's pretty stable, temperature stable is really kind of the key of what you're looking for with it. Could it be used in both ends, even if the manufacturer requires a different type of lubricant on the other end? Is that something that you all would say would be a
Well,
good idea?
that if the manufactured lubricant, if they have if they have a specification on there and they give you a type of lubricant that's in there, there's a good chance, if it is not a polyurea grease, it will not mix with polyurea grease. Since polyurea only mixes with calcium, it only mixes with a calcium complex grease. There's a good chance that putting polyurea grease in it may be a mistake.
Okay.
If they specify a type of grease, then I would put that type of grease in it.
So, kind of my next question is, when you all rebuild a motor, would you put polyurea grease in both bearings to start out brand new if you had to?
If the manufacturer has specified a particular lubrication for it,
That's kind of
we try to go back with that, because usually that's an engineered specification. And there's some mineral, there's some lubricant, there's something in there that is engineered into that piece of equipment. So we always try to go back with what is tagged on the motor. And we try not to remove any of the tags that are on the motor. So that all the motor tags and badging needs to stay with that motor from day one. Sometimes you send a motor out and it comes back and the tags have been removed and a different kind of tag's been put on it. And well, from that point on, there's always a question in your mind is, what was the real one? You know, what was on the real tag? What was the temperature rise? What was the insulation? All these things that are on the original tag need to stay there. When we rebuild a motor, most motors that you buy come out with a Class B insulation. When we rebuild a motor, we go back with Class H. And that is a high enough temperature that we're never going to reach it. And so we're actually ensuring that the work that we did to it and the insulation that we put in it is going to be better than what it was originally. Now, there are motors that come out with Class H insulation, and we go back to Class H. And H is about the highest for the standard that we operate under. This little handout here is pretty simple, and it won't take you very long at all to go through it. And it tells you some pretty good information about sealed bearings, shielded bearings, and open bearings. Open bearings require the least resistance to rotate. Shielded bearings are about the same as an open bearing. A sealed bearing requires resistance to operate, and also the seal generates heat. You put a new bearing in, it's a sealed bearing, and you spin it up to 3,600 RPMs, and then you shut a motor off and you feel the shaft will be hot, and it's just from the seal contact. There's applications where a shielded bearing is the best thing to do. There's applications where an open bearing is the best way to go. In the oil field, a lot of times, since the condition these motors work under, they're in such dirt, dust, chemicals, rain, a lot of times we will put a sealed bearing in. And if the lubrication is applied to the back side of the bearing, we will leave the seal on the front side. And it helps keep out the dirt, the water, anything else that's gonna come in. We also try to put a slinger on the drive-in shaft. And as all a slinger does is, when the water's running down that shaft, when it hits that slinger, it throws the water off, instead of allowing the water to work into the bearing. The cooling of the motor, the fins on the outside, it's very important to try to keep those fins clear of debris and try to keep them clean. A buildup of dust on the outside of a motor might raise its temperature 20 degrees, its operating temperature, just because it can't exchange enough air or enough heat. The air that's coming off of the fan has got to be able to blow down those fins. If there's bird nests on them or whatever, all that needs to be kept clean. All this will help maintain the life of the motor. You got to keep the temperature within a range that the lubricant can handle. I've seen motors come in that the fans have been broken off of. Maybe for some reason it's lost a fan blade at one time or another, and then it continues to operate. Well, if you lose a fan blade, you've lost the dynamics of the air moving across, plus you've thrown the rotor out of balance. A little bit of balance in the rotor will kill the bearing too. So, anything else anybody got to say?
When a bearing fails, talk about what kind of temperatures the motor can see when it fails, and is there any collateral damage? Can that damage the winding?
The worst that can happen, it's all bad. If a bearing fails and say the balls fall out of it, they break, they melt, they come out of it. Well, the shaft itself has probably seen maybe 2,000 degrees. So the metal in that shaft can be weakened. Also, the end belt that holds the outer race, the race will spin inside that end belt. Now it's enlarged it. So to allow it to take another standard bearing, you have to machine it back out round and then sink a sleeve in it and then machine the sleeve down to the proper tolerance to fit the outer race. The next thing that happens is the inner race spins on the shaft. And the inner race, if it spins on the shaft, it can friction weld to the shaft. Now the only way you're going to get it off of there is with a cutting torch, and then the shaft will have to be re-welded and then cut back down. The welding process that we use is the same thing that they use for repairing a crankshaft. It's like a MIG welder that's immersed in a flow of flux. And so it's pulling the heat away from it, and when they're finished welding it, it looks like the string on a fishing line, or on a fishing reel. It just winds back and forth, the welding bead. So when they machine that back, there'd be no air pockets in it, it'll be clean. And that is the best way to do it that we've been able to find. There's other ways of remanufacturing shafts, flame spray, and there are some high performance epoxies that are applied. But actually doing a controlled temperature weld to the shaft we see less failures. Matter of fact, I don't think we've seen a failure this year.
So we got, I'm making this number up, we got 300 motors out here in a 20-mile radius. Some of them are in good shape, some of them are in bad shape, but we know they're all deteriorating. Different rates of speed, but they're all deteriorating. What can I watch for to help me understand when I need to pull the trigger to pull that motor off? And if I miss that trigger and the motor goes to fail, kind of what's the difference in repair versus after failure, what it looks like replace?
If you pull a motor before it's, say, a bearing is completely failed. If the bearing completely fails, the rotor itself will drop down on the stator. It'll drag on the stator, Usually when it drags on a stator, you're looking at a rewind, you're looking at iron work to repair the stator. Possibly the stator could be ruined.
Right.
Also, the temperatures that it's going to reach inside while it's dragging can cause the core itself, the iron core, to lose its conductivity. In other words, it will saturate too quickly and you won't be able to produce the horsepower.
Right.
You know, you could take a motor that, say it was 100 horsepower, and after a good rotor drag, you may only be able to get 85 horsepower out of it. You may still have the same current, but you're not going to produce the horsepower, because the horsepower is the amount of copper versus the amount of iron. That's the law of that's just the law of motors. And I think the best way to keep an eye on it is through temperature. If a bearing's running too hot, then a person needs to shut down and find out why.
Can I feel that, or do I have to measure it somehow?
Well, I'd say a person would have to measure.
Okay.
And the outside skin of the bearing, your outside skin of the motor, is going to be as hot as the interior of the motor. On an energy efficient motor, the outside skin will always be much hotter than a pre-NEMA motor. A pre-NEMA motor with all the iron around it contained the heat better and ran cooler. An energy efficient motor, by cutting the amount of copper down, the amount of iron down, the castings down, the motor itself is running at the same temperature, but they can't contain the temperature, so they're doing their best to move the temperature out to the fins where the temperature can be removed by the airflow.
So you could have a motor, say, reading 200 degrees and it'd still be fine?
That's correct. That's correct. Under full load.
Now, well, what if you're getting different readings at different points of the motor? Say you're getting 130 at the front bearing, 150 at the rear, and on your windings on the outside of the motor, you're getting anywhere, 180 to 200.
Your bearing temperatures ought to be running within 10 degrees of what your stator temperature is.
Okay.
Now, and that's under full load. And the best way to know this is by trending. In other words,
Over time?
yeah, this particular motor, I've taken a heat gun, and I know that this particular motor under a full load, this is what I'm getting out of it. And you make a note of it. And 4 months from now, when you go back out there, you do the same thing. Vibration analyzer, if a person gets good with a vibration analyzer, they can put it on a bearing cup, and they can pick spikes up and then put lubricant in it. If the spikes drop, they'll know that it was low on grease, because you're actually pulling vibration out of it by insulating the grease. So that's another way. But vibration analyzers are, the graphs are a little bit of black magic. You know, if you looked at any of them, I don't quite get it. If you find somebody who says that they know it, and you actually pin them down, it doesn't come out the same. You know, it's I've tried to understand it myself, and I've had a very difficult time at trying to pin this down and understand why. And the engineers that build these machines, they'll swear that they know how it works, but they've never been able to get it across to me. But I do know, if you're doing a vibration analysis and you show a spike and you can apply grease to it and the spike went away, then that is an indication that that particular bearing was running too dry. Go
Can
ahead.
you briefly explain the OWP, or the motors with the slip, and how the slip relates? Just
The slip is related to the skew in the rotor. And the skew in the rotor is, rotor bars can be straight from one end to the other, or they can be maybe a 15-degree angle. So your stator bars will be straight. A skewed rotor will have a bar that may be making contact with 3 rotor bars. So when you start, do a cross the line start on it, when the magnetism builds and it starts to pull, it'll pull off of one bar to the next bar to the next bar. So it gives you a more gradual start. Where if all the rotor bars are straight, the minute you hit it, it's going to go to full load and be at operating speed.
Would slip extend bearing life?
Any soft start will extend bearing life.
What applications would you recommend OWP on?
Well, anything that has to start under a load. Yeah, if it's loaded. Now, if you're pulling like a pump jack, where you're gonna start and it's gonna start moving and it may not have a full load on it. You can be across the line start on it, it's not gonna make a difference.
Okay.
But, you know, it's got a load on it. If you can take that inrush surge out of it, you're gonna be safe. That's a stress to take away. When you're storing motors, you were talking about storing motors, having a warehouse full of motors. A motor that's been sitting in a warehouse for a length of time, every 60 days, the shaft on that motor should be rotated, maybe 6 or 8 rotations. The grease that's in there, the oils are settling out of it when it's sitting still. As you rotate it, it's going to pull fresh grease up and it's going to keep the races and the balls stay covered. And another thing, if the motor's very big, say it has a rotor that's 1,000 pounds, when it sits still, the tendency of the rotor is going to be to sag. You start it up, and now the rotor's way out of balance. So you should rotate it every so often to keep that sag from appearing in it.
So I think earlier on you said kind of an industry average is 50% of motor failures are mechanical related bearing failures, like we've been talking about. Just based on your experience with NBI, what's our statistic?
Oh, yours is easily 80.
Okay.
Easily 80. But you know, on the other hand, I don't know how long those motors have been out.
Right.
I'm just saying by what comes in the door.
Right.
Now, if 50% of the failures are bearing related, that doesn't mean that 50% of your motors out there have got a bearing problem. It just means the ones that have failed that come in the door is what there may be motors out there that have been running for 15 years or better.
Say if you had an 8-year run, that's really good.
That's yeah, that's great.
Depending on the length of your run time.
Sure.
Based on that also.
Yeah. And, you know, there's another kind of an industry standard that insulation itself, the insulation within a motor, if that motor never ran and it sat for 10 years, the insulation within that motor may not be good enough to stand the load. And that's from oxidation. So,
That was a meter than
Hmm?
Check that was a meter.
a megger would tell you that, or a high potential hypotony. Yeah. And that's where you need to go with that.
Have you addressed, is it a correct assumption to say that variable speed drive has more tendency to cause bearing failure than what's your opinion of variable speed drives?
Variable frequency drive is on anything that has a load on it. So you can do a soft start and you can ramp up your speed and bring your speed down slowly. Is going to be easier on the motor overall. The bearings, the shaft, the windings, all of it's going to be easier. A variable frequency drive, however, needs to be installed properly, it needs to be grounded properly. The ground on a variable frequency drive is very, very important. The motor and the drive need to be connected with the same ground wire. You don't go from the motor to a bus bar, and then from a bus bar to a drive. You need to run the power wire all the way back and the ground wire all the way back to the drive. And in some cases, on a variable frequency drive, normally you're looking for a spot, an RPM, that what you might call the sweet spot. In other words, that pump is going to be putting out what you want out of it. And if that sweet spot is in a place where that drive is pulsing real hard, then a lot of electrostatic energy is going to be going into the rotor, and it's going to try to find a way to ground. And that's where a shaft grounding system is necessary. That's, some of these bearings I've got up here will show that.
So you would recommend the most important thing is proper ground?
Proper grounding is
I just wanted to throw that out.
that is, yeah.
So your biggest complaint is with the electrician? Did you hear that, Jeff? The next one's on you. Thank you.
Jack keeps us out.
I know, I was kidding.
You know, phase balance is also pretty important. You know, you need to know that, especially out here in the oil field where you might have a lot of real strange electricity getting out to where it's going. You know, you need to be sure that your phases are balanced. Because if you know a motor that has a low leg or a high leg, you know, that's going to produce an internal vibration, and the vibration eventually is going to get the bearing.
So just here, I'm driving towards the question of rebuild or replace. And so I'm going to make up a scenario for you.
Okay.
Scenario A is we catch a motor with pending bearing failure before
Or the race spins on the shaft, or the end mill.
but before there's internal damage to the windings or anything else. Or maybe we let it run to fail and the motor won't rotate anymore.
Sure.
Given kind of those two scenarios, what, just on an average 20 horsepower motor, what's it cost to replace the bearings and get that motor back to good?
Glad you brought 20 horse up, I've got the numbers in my head.
All right.
The new motor's a little over $1,000 for China made, $1,300 for a Brazilian.
That's the
The
price
rebuild
for a
on
new
that,
motor,
if
right?
it needs no machine work, just rewind the bearings to 638. There's still a savings there, but if it needs an in-belt sleeve or a shaft built up, no, it's junk.
Okay.
In the shop, we try to shoot for about 65% of new.
So if you look at this little handout here, we ought to buy a new motor. If it's
That little handout there, I think, tells you
70%.
70%.
Yeah.
It'd be better to buy a new motor than rebuild it.
Correct. Correct.
How many times can you rebuild a motor before?
I've got some motors that we rebuilt one this year that was built in I think it was built in 1928, and it still came out.
So how many times has it been rebuilt?
Oh, it's been rebuilt probably 7 or 8 times.
Cases that.
How many times can you actually rebuild before you
It's really kind of an indefinite. I mean, it depends on what kind of failures you have. Because, yeah, and it's your laminations, the iron stack in the motor, the laminations are insulated by kind of an anodizing process, kind of an acid dip process. And as that motor, every time you rebuild it, you have to apply heat to it to burn the varnish out of it. And every time you do that, there's a chance, if you don't do a controlled burn on it, there's a chance you're going to burn that insulation up. Once that insulation burns up, then the iron will saturate and it will not produce horsepower anymore. The current will go way up. The motor is, but what we do is we do a core test on the motor before we take the wire out of it. And then we do a core test on it after we burn it and pull the wire to determine if the insulation or if the core itself was able to stand the burning. Because if it didn't, there's no point in going any farther. That's when you need to hold your hands up and say, we need to replace. We're at a point here where you're going to go backwards if you do this. Now, no matter how this works, there are some applications where the customer will have to rebuild that motor time and time again, because modern motors will not replace some motors that came on machinery that were built 30, 40 years ago. And we see that all the time. And you can restack a motor where you pull all the iron out of it and you have new iron cut for it, and then you restack it. And you can rebuild one countless times. You can restack the rotor itself. Right, but the cost is really prohibitive.
Okay, any last questions?
One question on the rewinding efficiency. Isn't that assumption really driven by how much that motor operates? So if I'm on a well that operates 1 hour a day, it's a different answer than one running 24/7? So I could have a lower efficiency and accept it because it's a cheap cost and I don't use it much.
Certainly, well, it's a customer expectation. It's what the customer expects out of that motor. You know, when you take it to a shop, we're reading what's on the nameplate. And that's what we're trying to go by. But if you're, say this motor was a 10 horsepower motor and you're only requiring 3 horse out of it, you can get by with a lot of things.
And you might accept lower efficiency
Correct.
on a 1 hour a day deal as opposed to a 24/7.
That's exactly
If
right.
you can't match the frame size and that's the only motor that you've got, that would be a difficult reason to do it, because that's a fit to a pump or a fit to
That's
something,
correct.
perfect fit, rather than try to find one or shim it.
We run into that on cranes and rubber mills and things, big machinery, mills, lathes, things that you can't buy motors
You
for.
can't buy them anymore because they don't make the frame size anymore.
Derek, do you have anything you want to add as we kind of wrap up?
Well, hopefully everybody found this at least educational.